All right, welcome everyone. So today we're going to be looking at Learning Outcome D1. But before we get into that, just a few announcements um, about the exam. So I really want everyone to take a look at what questions they got marked wrong on, and don't forget you'll be able to try those questions again next week on our next exam for full credit. So it's kind of just a continual process of trying, learning from your mistakes, and trying again next time. So just keep that in mind. If you are marked with a progressing score on one of the questions, well, then you'll try that a question again on the next exam. All right, so today this is a fun one. This is a nice, it's a feel-good story. So today we're going to be looking at how to compute derivatives of basic functions. And we've before the past couple lectures, we've introduced the conceptual idea of what a derivative is. So it's the process of doing a particular limit. And that takes a bit of work to do. So we want a nice, easy way to be able to calculate derivatives quickly. And that's what we're going to introduce today. Some of our derivative rules, which are really going to simplify the process of calculating derivatives. So in this lecture, we're going to see how to do derivatives of functions that can ultimately be solved by using the sum, difference, or constant multiple rules in conjunction with our list of elementary forms. And to kind of put this into the context of what we were doing the past few lectures, let's talk about slope of a curve. And that's really all we're doing with a derivative, is the derivative measures the slope of the curve at any x value. And so in this slide, we're going to just consider two basic functions, f of x equal to mx plus b, and then f of x equal to b. And we're going to calculate the derivative of each of these. But we're going to do it conceptually. So for the first one, f of x equal to mx plus b, if we were to graph that function, as we've done over here, it's just the graph is a line. So it's just a line, and the slope of it it's written in mx plus b form, so that m value, that's our slope. And so when we think of the slope of the curve here, at any x value, well, it's a line. So the slope at any point on that curve, the slope is always m. So what does that mean for our derivative? Well, if we were to calculate f prime, what f prime does is it measures the slope of our curve at any x value. And so f prime here is just going to equal m. Now what about f of x equal to b? Well, where b is a constant, well, that's also a line. So if we were to graph a constant function, y equals b, that's just a horizontal line. And what's the slope of a horizontal line? Well, it's just 0. So it's just flat. And so if we were to consider what is the slope of that curve at any x value, so pick any point on that curve that we just graphed. At any x value, we're interested in what the slope is. And at any x value, any point on that curve, the slope is just 0. So when we actually think about what the derivative is, well, f prime really just is measuring the slope of the curve at any x value. And so f prime in this case would just be identically 0. It's just equal to 0. And so these are two kind of basic examples for what the derivative would be when our function is a line. And as we're going to see in the rest of this learning outcome, we're going to develop a set of rules that will allow us to do the differentiation calculation that quickly, where it's basically one line of work. We just write down the answer, basically. So everyone's been asking for it, and here it comes. So brace yourself. Boom. Power rule. If we have a power function, and power functions are the ones we look at the most in a lot of applications. Everything kind of boils down, as you'll see in Calc 2, everything really boils down to power functions. So being able to differentiate a power function quickly is going to be important. So let's read through what this says. We have x to the power r. So x is our variable, and our exponent here, we've written it as r, but this can be any number. So r is just going to be just a number, and our variable is going to be, right where the x is, the base of this power function. So how do we differentiate this? Well, you can just remember the power rule and just kind of remember the formula and apply it each time. But we tend to think of it as more of like a process. So how do we differentiate? All right, so we're going to start by writing f prime of x. And the very first step that we do when we're applying this power rule is to take our exponent and put it in front. So we're going to take r and put it in front. That's our first step. All right, once we've done that, then we just keep our variable the same. So our variable is x, it's going to stay x. And then in the exponent, what do? Well, we're going to subtract 1. So we're going to take our old exponent, which was r, and we're going to subtract 1 from it. And that's sort of the third little step here. So the process is you bring down the old exponent, put it in front, you keep your variable the same, and then you subtract 1 from the old exponent to get your new exponent. And that's really the process. So, you could just remember the formula. I tend to think of it as more of just a process of this is what you do. All right, so let's see a few examples. All right, so we've looked at the function x squared before, and let's see how the power rule looks when we apply it. So first, when we notice here, our exponent, it's a number, and it's 2. And so when we go to do our derivative, when we go to calculate f prime, switch colors here. When we go to do f prime, how does this work? Well, we bring down our exponent, 2, put it in front, keep our variable the same, so it stays x, and then we subtract 1 from our exponent, so 2 minus 1. And then if we simplify that, we get 2 times x to the power 1, and then we don't normally write exponent of 1, so we just kind of leave that off. So the derivative here is just 2x. All right, let's try another one, x cubed. Very similar type setup here. Here our exponent is 3. So when we go to calculate our derivative, f prime in this case, what are we going to do? Well, we'll bring the exponent down, put it in front. So we bring down the 3. We keep our variable the same. So it was an x, it stays an x. And then we subtract 1 from the exponent. So we have 3 minus 1 up there. So if we simplify, we get 3x squared. So there's our derivative f prime. Derivative of x cubed is just 3x squared. Now, in practice, this is almost too much work. So this middle step here, once you get the hang of these, you're probably not going to be showing this. And I won't be showing it in lecture either. So this step here where we're actually showing the minus 1 up in the exponent, we're showing that here because this is really the first time we're using the power rule. But once we get the hang of this, that step we normally leave out. You just do it in your head. But, you know, as you're getting used to using this, if you want to show that step, that's perfectly fine. And if the exponent is kind of complicated, sometimes it doesn't hurt to show that step as well. You know, but once we get going on these, for a lot of these functions, you're going to have the function, and then you're just going to write down the derivative. So there's not going to be too much work to show on some of these. All right, so what about the next one, square root x? So that as it's written, that doesn't look like a power function. So the first thing we need to do is to rewrite it. And this is going to be a common strategy. Whenever we see a root sign, we're going to rewrite it as an exponent. So when we have the nth root, we can write that as raised to the power 1 over n. So for our case here, we're going to rewrite this square root x as x raised to the power 1/2. So now it's a power function. We have our base term x, we have our exponent, which is just a number. So now we just go and do the power rule. So we bring down our old exponent, which is 1/2, put it in front, keep our variable the same, x, and then we subtract 1 from the exponent, so 1/2 minus 1. And then if we simplify, we get 1/2 times x to the negative 1/2. And this is perfectly fine to stop here. Now, we might have the occasion sometimes to kind of rewrite that function just a little bit further. So when we have a negative exponent, we can write that as a reciprocal. And then sometimes it might even be helpful to take that exponent and convert it back to a root function. So, you know, we might have the occasion to go a little bit further with this and kind of write it, instead of a negative exponent, write it as a fraction. So 1/2 times 1 over x to the 1/2. Or if we want to go even a little bit further, rewrite that x to the 1/2 back as a square root. So we could even write this as, say, 1 over 2 times square root x. So sometimes we might need to kind of rewrite these after we've done the differentiation. But for purposes of just getting the derivative, it's perfectly fine to stop with that 1/2 x to the negative 1/2. Perfectly fine to stop there. All right, let's try one more basic power rule here. 1 over x. The function 1 over x. And so as this is written, it's a quotient. It's 1 divided by x. So our strategy for these is to rewrite that fraction with a negative exponent. So these last two, the root function and this fraction, these are going to be common techniques for for how to handle these functions in terms of differentiation. Root function, rewrite it as a power function. A fraction like this, try to rewrite it as a power function. So we're going to write this as, as x to the minus 1 power. So now it's a power function, and we can just go do our power rule. So what do? Bring down the -1, bring down our exponent, put it in front, keep our variable the same, so it's an x, stays an x, and then we subtract 1. So -1, and then we subtract 1 from it. And if we clean that up, we end up with negative x to the -2. Or if we wanted to go a little bit further, we could rewrite that negative exponent back as a fraction. Sometimes that's helpful. So we could write this as, say, -1 over x squared. But like we said, perfectly fine to stop here. And actually, as we'll see later, sometimes we want to compute the second derivative or the third derivative. So sometimes it's actually better to stop there where you still have your exponent written as a negative. All right. So that's the power rule. So as is, we can differentiate power functions. But we generally work with kind of combinations of functions. So it's not just x squared. We have numbers in front of the x squared. We might add some of these functions together. And so there's derivative rules that tell us, how differentiation works for when we start combining these functions. And that's what we're going to see next, is the constant multiple rule. So this gives us a differentiation rule for what happens when we have a constant multiple of a function. So k is just a number. It's a constant. So what do we mean? So we have k times f of x. K is a constant. We can think of f of x as our function, but really it's our variable term. That's where the variables are. And then in between our variables and our constant there's a multiplication sign. So we're multiplying a variable by a constant. And what this derivative rule tells us is how differentiation works for that. And essentially what we can do is we can take that constant multiple and we can move it outside of the derivative. And that's what this does. This tells us we can bring the constant multiple, that number in front, we can move it outside of the derivative. All right, so we have a special case of this in terms of, in the context of power rules. So let's see how it works with the power rule. So if we have just a basic power function, x raised to the power r, when we apply the derivative to that, what the power rule says is we get r times x to the r minus 1. Now, what would happen if instead we had a constant times a power function? So we had a times x to the power r. So a is just a constant here. Well, what this constant multiple rule says is it says we can focus on just the variable term, differentiate that. So derivative of x to the power r is just r times our variable raised to the power r minus 1, so just the power rule. And then the constant multiple just kind of stays in front. So this is really a special case where we have a constant multiple times a power function. How does it work? Well, we differentiate the power function just like we would with the power rule, and then the constant multiple just kind of stays in front. Doesn't do anything. It just stays there unchanged. So let's see some examples of this. So let's look at the function 2x to the power 5, and we're going to differentiate this. So just to kind of diagram it again, we have this constant 2 that's in front of our variable term. We have x to the power 5 here. This is our function. This is our variable term. So this is where the x's are. And then in between those two, it's not really written. We don't generally write the multiplication sign there, but it's implied is that there's actually a multiplication in between there. So we have a number 2 times our variable term. So what this constant multiple rule says is we can bring that 2 in front of the derivative. We can move it outside of our derivative process. So we could really think of this instead as just 2 times the derivative of x to the power 5. So that's our constant multiple rule. We've moved that constant outside, put it in front. And then this just is basic power rule now. So how do we differentiate that? Well, the 2 stays in front. And then applying the power rule to x to the power 5, we bring down the 5, keep our variable the same, and then we subtract 1 in the exponent. So it's 5x to the power 4. And then if we simplify that, we can take that constant multiple, multiply it with the 5, just to consolidate a little bit, and we get 10x to the power 4. All right, so like I've said before, once you kind of get the hang of these, you're probably not showing any of that work. You're probably just going right to the answer. Once you get the hang of these, you're probably just going right from the function, and then you can just write down 10x to the power 4 as your derivative. But as we're just starting out here, it's okay to show some of these extra steps. All right, let's try another one. A little bit more complicated. So we have the function x cubed over 4. And as it's written, there's actually division. It's x cubed divided by 4. So for these, and for a lot of these power function type ones, an underlying strategy that we want to use is we want to rewrite it. It's going to be helpful. We want to rewrite it in the form that we were just talking about, a times x to the power r. So we want to move all of our constant terms. We want to kind of separate them a little bit, group them all together, and put them in front of our x terms. So if we do that for this function, I would rewrite that x cubed over 4 instead as 1 over 4 times x cubed. So what we're doing there is it's a property of fractions. So when we have a divided by b, we can rewrite that fraction as 1 over b times a. So division is the same thing as multiplication by the reciprocal. So that's what we've done there. And that 1 over 4 is just a number. So we can move that out front of the derivative now. So we can put that in front. So we can move the 1 over 4 in front, and it's times the derivative of just the x cubed. And now the derivative of x cubed, that's just the power rule. And we did that one before, and we saw that it was 3x squared. So we have 1 over 4 times 3x squared. And it's helpful to just consolidate all of the constant terms into kind of one fraction. So we could go a little bit further and write this as 3 over 4 times x squared. And so when you're looking at that number in front, it's helpful to just think of that 3 over 4 as just a number. It's 3/4. It's 0.75. It's just a number. So we have a times x to the power r here. We have this, our result here. Always try to keep going back to that format of having a constant term times your variable term. So a times x to the power r. All right. So some little examples there involving the constant multiple rule. Let's try a few more just for extra practice. Doesn't hurt. So let's look at the derivative of negative 3 over x squared. And again, we're kind of going with the strategy of writing that as a constant times our variable term. So we kind of want to just separate them just a little bit. And that's our strategy. We want to separate the constant terms and the x terms. So we're just going to rewrite this function before we do any derivatives. The negative, we could think of that as like a negative 1. We have the 3, so we could write this as negative 3 times 1 over x squared. Now that 1 over x squared, that's a fraction, so it's not written as a power function yet. So we have to go through and rewrite that using a negative exponent. So before we're doing any derivatives, we just want to rewrite that 1 over x squared as a negative exponent, get it into the power function form. So we'll write this as the derivative of negative 3 times x to the negative 2. So now it's in that format, a constant times a power function. And so now we can apply our constant multiple rule. And really how this is going to work, we're not actually going to always be specifically showing that constant multiple rule step. So what we're going to do is we're just going to identify our variable term here. So x to the minus 2, and we're just going to differentiate that like usual. So what's the derivative of x to the minus 2? Well, you bring down the 2, negative 2, keep your variable the same, and then you subtract 1 in the exponent. So negative 2 minus 1. And then our constant term here that was in front, the negative 3, well, that just stays in front. So we're just going to put negative 3 in front here. So the negative 3, our constant multiple just stays in front, and then we just differentiated the variable term just like we normally would. And then clean up as needed. So negative 3 times negative 2 is 6, and then if we do the subtraction there, we get x to the minus 3. and I'd stop there. So really that's kind of more along the lines of how we're going to be using the constant multiple rule as we go forward. Is you're not going to be specifically showing it, you're just going to be kind of doing it in your head. All right, let's try one more with that approach. And here we have the function 5 times the cube root of x. So we see a root sign. First thing we need to do before we start thinking any derivatives is just to rewrite that root sign. So how do we do it? Well, we're still going to have that 5 in front, and then the cube root is the same thing as x raised to the 1/3 power. All right, so we have that format now. Constant times a power function. So what do? We identify our variable term, which is just x raised to the 1/3. Differentiate that like usual now. So we bring down our exponent, put it in front. So 1/3 goes in front. Keep our variable the same, x. And then we subtract 1 from the exponent. So we have 1/3 minus 1. And if you have to show that, that's fine. So sometimes when you have these fractions in the exponent there, it doesn't hurt to show that -1 step, just so you don't have to do everything in your head all at once. So that's our derivative of x to the 1/3 power. And then our constant multiple here, the 5, well, it just goes in front. So our constant multiple just goes in front, and we differentiate our variable term just like we normally would with power rule. And there it is. That's our derivative, but we could clean up as needed. So usually it's a good idea to try to get back into that constant term times your variable term. So what I would do is multiply the 5 with the 1/3 and put that as 5/3. And then that x to the 1/3 minus 1, just clean that up. It'd be x to the -2/3. And if you needed to, you could go a little bit further, but we'll stop there for that one in terms of simplifying. So really what we've seen here is that when we have a constant term, times the power function, how do we go through the derivative process? Well, we have our power function, and we basically do the power rule like normal. So basic power rule there, we're differentiating. And then the constant multiple that we have in front there just kind of stays in front even after we've done our derivative, differentiated using the power rule. So that's kind of the format, how we do this. Is the constant multiple, it's kind of sticky. It just sticks around as you go through the derivative. Kind of sticks to the variables. All right. So that's constant multiples. But we want to be able to look at what happens when we add or subtract these functions with each other. And so there's one more rule that we're going to look at for this learning outcome, and that's the sum and difference rule. And they're really the same thing. So we could just think of it as the sum rule. So what this says is it tells us what happens when we have two functions added together and we want to calculate the derivative of that. So on the left side here, this is the derivative of the sum of two functions. So we have function f plus function g. We're adding them together, and we want to be able to calculate the derivative of the result. Have function f, we have function g, we're adding them together, and then we want to differentiate the result. Well, how does that work? And it turns out it works very nicely with derivatives. So what this rule says is that on the right side, we can just do the derivative of f, do the derivative of g, and then just add those results together. So it's equal to the sum of the derivatives. So addition and subtraction, they play very nicely with differentiation. So really what this rule says, another way to think of this, is we can split up the derivative at addition and subtraction signs. Addition and subtraction, they're really the same operation. So really this formula works just as well if we were to have like a subtraction sign in between. And sometimes we call that, when we do have the subtraction specifically stated, sometimes we call that the difference rule. It's really just a special case of the sum rule here. All right, so and so it also holds for subtraction. That's essentially it. We call it the difference rule. All right, so we're going to see how this works. But it's just important to consider just a little note here. We want to consider the difference between two functions. Maybe difference isn't the best word. Well. So what we've seen before is the constant multiple rule. So k times f of x. What this new rule is saying is what might happen if we have f of x plus a constant k. So, these look, in practice, these will kind of look similar, and it's just important to consider what the distinction is, what makes these two functions different. And so this one here is constant multiplication. And this one here it's a sum. It's a sum of f of x plus k. So how we differentiate these two, even though they kind of involve the same ingredients, how we differentiate these is going to be different. So it's just kind of, we'll keep that in mind as we go through this. Just if we have constant multiplication, how that works is going to be different than just adding on a constant at the end. And we'll see that in a few examples. So let's look at first the function x cubed plus 5x. And this is just going to be just regular sum rule that we're going to apply here. So let's see how the sum rule works. And what we see is that in the middle, right in the middle there, we have a plus sign. So what the sum rule says is we can split up the derivative and instead just do the derivative of x cubed, the derivative of 5x. So we just do the derivative of each of the pieces there, and then we just add them together. So derivative of x cubed plus the derivative of 5x. And now each of those is something we've done before, either power rule or constant multiple rule. And so the derivative of x cubed is 3x squared, and then the derivative of 5x is just 5. So it might be helpful just to recall that the derivative of mx, kind of looked at that one right at the beginning, is just the slope. So it's just m. And another one that's going to be helpful, and we'll see this in the last example here, but we've also done this, the derivative of just a constant is 0. Okay, so let's try another one of these, and we just recalling some of our basic derivatives that we first looked at when we started talking about this topic. Let's try another one. So let's look at x to the power 4 minus 3 over x squared. We want to differentiate that. Now we see subtraction there in the middle. So what the sum rule tells us, or sum or difference rule, is we can split up the derivative wherever we see addition or subtraction. So we could write this as x to the power 4. Just do the derivative of that. Then do the derivative of 3 over x squared. And because there was a subtraction sign right in the middle there, we just do the subtraction of those two, the difference of those two derivatives. All right, so what's the derivative of x to the power 4? Just power rule. So we bring down the 4, keep x the same, and then subtract 1 from the exponent, so 4x cubed. Then the derivative of 3 over x squared, we just did one very similar to this. So kind of see the previous example, one of our previous examples here, where we basically did the derivative. I think it was negative 3 over x squared. And what did we get for that? Well, you'd get negative 3 over x cubed, or negative 6 over x cubed, rather. And then double negative becomes positive. So we're just kind of showing how this works. If we were going to write out all these steps, how this works by doing the sum or the difference rules. But in practice, we don't generally show, say, we wouldn't show this step. Once we get the hang of this, we're not going to be showing this regularly. So instead, we do most of this work in our head. And the process, we kind of give it a name. We call it term-by-term differentiation. So when we're presented with a function, each term here, let's look at the third one, the 2x to the power 7 minus x to the power 5 plus 8. When we look at that, we just think of each of these terms, or we think of each of these pieces as just different terms. We have our first term, which is 2x to the power 7. Then we have subtraction. Then we have our second term, x to the power 5. Then we have addition, and then we have our last term, which is 8. And so what we're going to do is we're going to just differentiate each of those terms and just go down the line. So for the first one, let's just circle our variable term there. It's a constant multiple, so it's 2 times x to the power 7. Let's differentiate our, and actually let's introduce just a little bit of a shorthand notation here. So let's just rewrite our function. And what we're going to do, we're going to go differentiate term by term, but what we're going to introduce here is, instead of writing ddx a whole bunch, a bit of shorthand that we're going to use is we're going to use brackets with a little prime symbol. And that's just going to be shorthand for derivative. So when we look at this function 2x to the power 7, the first term, let's just look at the first term, and we know that we can just apply the derivative just to the variable part. So that constant multiple 2, we can just put it outside of our brackets there. Then we go to our second term. We apply the derivative just to the variable part. And then we go to our third term, and since there's no variable, we just apply the derivative to, everything that's there. So then we go through and do the differentiation. So derivative of x to the power 7, power rule, so bring down the 7, keep x the same, and subtract 1 in the exponent to get 6. Then we have subtraction originally, so we're going to keep subtraction, and then do the power rule of x to the power 5. So bring down the 5, keep x the same, subtract 1 from the exponent, so 4. And then finally, the derivative of a constant by itself is just 0. So cleaning that up, we have 2 times 7x to the power 6, and that gives us 14x to the power 6 minus 5x to the power 4, and then we don't normally write plus 0 at the end. So again, that's probably even more work than we're going to be showing once we get the hang of these. But just to kind of illustrate how the sum and difference rule works, we're showing a little bit more there. And then just one thing to keep in mind is this 2. There's a difference here between this 2 and this 8 term here in our function. So the 2 is sort of attached to a variable. So that's why it makes it through the derivative process. So when it's a constant term is attached to a variable, it kind of survives and it makes it through the derivative process. When a constant term is unattached, so it's not attached to a variable, when we do the derivative of just a constant by itself, derivative just makes it into 0, kills it off. So just a little bit of a distinction there. When we have a constant multiple, so when we have a number in front attached to a variable, it's going to make it through the derivative process. We'll still see that 2 later on. But when it's a number just by itself, off on its own at the end there, the derivative process gets rid of it, makes it to 0. All right, let's talk about what happens with other variables. And, we don't always use y's and x's for our variables. It doesn't matter. The process is still the same. So, whether we're differentiating y equals x squared or v equals t squared, the power rule still works. So, for instance, if we were going to calculate the derivative of y with respect to x, we might also just call that y prime. Power rule tells us that derivative is 2x. If we were using different variables, same thing, just different variables. So derivative of v with respect to t, we would write as dv dt. We might also just write it as v prime, and it's going to be basically the same thing, same power rule. So 2 times t. So kind of to keep track of what's happening with these different variables, a lot of times we'll say this when we say this. When we say dy dx, that's really saying the derivative of y with respect to x. So it's the derivative of function y with respect to variable x. So same for this other derivative, just different names. So derivative of v with respect to variable t. So a lot of times we'll abbreviate with respect to as WRT. And so we've seen this notation before, the prime notation or the Leibniz notation, the dx dy over dx. So the prime notation is a good shorthand, but it's not as descriptive as the dy dx. So there are some benefits to using dy dx, but there's more there. It's not as nice and short and clean looking. But it does give us some more information. And so this y here, this is really the expression or the function that we differentiate. So it tells us what we're differentiating. We're differentiating y. And then the x there, that tells us what variable we're actually differentiating with respect to. So it tells us the independent variable. And then the d's, they mean we're doing the derivative. All right, so when we look at in the example here, we're going to compute the derivative of that function a t squared plus s times t to the minus 1 plus s squared. There's no numbers there. It's all letters. So how do we interpret that? Well, we look to our notation and we see that it's dt. So that's really telling us t is the variable we're going to be differentiating with respect to. So what does that mean? It means t is our variable. And then any of those other letters that we see, we're just going to treat them like constant terms, just like as we would if it was, explicitly a number. So the a that we see and the s, those are just going to be treated like constant terms. All right, so let's do this derivative. So let's just rewrite our function, at squared plus st minus 1 plus s squared. And we know t is our variable, so we're just going to go term by term and apply the derivative to each of the variable terms that we see. So in the first piece here, we're going to apply the derivative to t squared. In the second piece, we're going to apply the derivative to t to the minus 1. So a and s are just constant multiples, so that's why we're putting them outside of the brackets. And then there's no variable term in that last one, so we just apply the derivative to the whole thing. And then we go through and just do the differentiation. So a is a constant multiple, so it's going to stick around. Derivative of t squared is just 2t, so there it is. We're done differentiating that first term now, so we put the plus, and we go on to our second term. Again, there's a constant multiple, s, so that's going to go in front, and then we just do the derivative of t to the minus 1. So that'll be negative 1 t to the negative 2, just power rule. And then finally, we're done with that derivative of that second term now, so there's a plus sign, and then we go to our final term, which is just s squared. And s squared is, in the context of this function, is just a constant term. So when we differentiate a constant term, it's just 0. So plus 0. And so if we clean that up, little bit we can do. We could write this as 2at minus s times t to the negative 2. And then we don't write the plus 0. All right, so that's how we handle other variables. We don't always use y's and x's. Sometimes we'll use t's. So the process is basically the same. All right. So that's power functions. So we've seen how to differentiate power functions and then all sorts of combinations of them, whether we add them, subtract them, multiply them by a constant. Well, there's other functions we're interested in. And so we have our table of elementary forms that we're just going to look at here. And these are the ones, it's just going to be easy to memorize these. So, there's no way around it. You just have to memorize these. So we have our 6 trig functions: sine, cosine, tan, cosecant, secant, and cotangent. And then that's the first column. In the second column, we have their actual derivatives. So like if we were to read the first entry here, what this is telling us is that the derivative of sine x is equal to cosine x. Derivative of cosine x is equal to negative sine x. Derivative of tangent is equal to secant squared x. Derivative of cosecant x is equal to negative cosecant x times cotangent x. Derivative of secant x is secant times tan. And then the derivative of cotangent x is equal to negative cosecant squared x. So there's 6 trig functions. It's better just to have these memorized. And just a note here is that when we talk about trig functions, the variable is understood to be in terms of radians. So just keep that in mind if you're going to be using a calculator kind of on your homework at all. When we're working with trig functions in this course, the variable is in terms of radians, not degrees. So when these derivative rules that we have, or these derivative formulas that we have here, they only work if we're talking in terms of radians. So just make sure that if you are using a calculator, make sure you do set it now. You don't need to use a calculator. On the exams, you're not allowed one. For web work, the entry block there is automatically configured to accept the variable evaluates these functions in terms of radians. So really, this might not be an issue, but it's worth mentioning that if you're going to be using a handheld calculator at all to kind of help on the homework, just make sure you set it into radians and not degrees. All right. So those are our 6 trig functions. There's also 6 inverse trig functions, and so there's just formulas for what those derivatives look like. And we'll see. We'll actually go through in the upcoming week. We'll prove most of these. But once we do that, it's easier just to have them memorized. So for instance, the inverse sine function, the derivative of that is 1 over the square root of 1 minus x squared. The derivative of the inverse cosine function is negative 1 over square root of 1 minus x squared. And then the derivative of arctan, or the inverse tan function, is 1 over 1 plus x squared. So the inverse trig functions, there is inverse cosecant, there is inverse secant, there is inverse cotangent. We're not really going to be working with those too much. So, these 9 derivative formulas here, I recommend that you memorize these. And then maybe, for the inverse cosecant and inverse secant, maybe for those, you just look those up. But it'll be helpful to have these 9 derivatives memorized. And just a kind of a little note here to help with that process of memorizing is that any of the trig functions that start with the letter C, they have a negative in the derivative. So if the trig function or the inverse trig function starts with the letter C, it has a negative in the formula for the derivative. So like cosine, it's negative sine. Cosecant is negative cosecant times cotan. Cotangent starts with a C, has a negative. It's negative cosecant squared. Also works for the inverse trig functions. So inverse cosine has a negative in front. So any of our trig functions or inverse trig functions that has a C in front, there's a negative in the derivative. So just a little, kind of a helpful little tip there for memorizing these. All right. So a few more that we're going to be looking at are elementary forms, are exponential and log functions. So derivative of e to the x is just e to the x. Derivative of kind of a more general exponential function, b raised to the power x, is b raised to the power x times natural log b. And then for log functions, we might look at just natural log x. So the derivative of that is 1 over x. Derivative of natural log of the absolute value of x also is 1 over x. And then more generally for log base b of x, the derivative is 1 over x times natural log b. So again, these are ones that you probably just have memorized. Get these memorized. And not too much extra to say here. Really, the exponential functions are nice, and we're going to talk more about this probably next week. But one observation here is that e to the x is its own derivative. Very special function. There's not many functions like that where the function and its derivative are actually equal to each other. And turns out they all involve e to the x. So in calculus courses, we'll see why this is next week, but e is an important number. And primarily for this reason, e to the x has the nice property that it's its own derivative. All right, so let's see these in action. So let's differentiate the function y equals 2 times sine x plus 3 times tangent x. And what do? Well, we see we have some constant multiples, and we have a plus sign in the middle. So how do we work with this? Well, just rewrite our function here, 2 times sine x, that's our first term, plus 3 times tangent x. And what we're going to do is we're just going to apply the derivative to the variable part in each term. So we're going to apply the derivative to the sine x, and then in the second term we'll apply the derivative to the tan x. And then we just go through and we look up what each of those derivatives are. So, once we get these memorized, we'll be able to just write down what the derivative is. But let's go for sine x. So what's the derivative of sine x? We find sine x on our chart, and the derivative of that is cosine x. So it'll be 2 times cosine x here. Then we have our plus sign, and then 3, and then we want to know what the derivative of tan x is. So we find tan x on our chart, and then we just look it up, and we see that the derivative of tangent is secant squared x. So we just fill that in. So the derivative here ends up being 2 cosine x plus 3 secant squared x. And that's really it. So these elementary forms, we can play the same games in terms of sum rule, difference rule, and constant multiple rule that we were doing with power functions. What about inverse trig functions? So what about the function f of t equal to 2 times inverse sine plus 3 times inverse tangent of t? Same idea. So let's just rewrite our function. 2 times the arcsine of t plus 3 times arctangent of t, or the inverse tan function. In the first term here, we apply the derivative to just the variable part, so the inverse sine function, inverse sine of t. Go to our second term, apply the derivative to just the variable part, so inverse tangent of t. And then we just look those up. So inverse sine, what is it? It's 1 over the square root of 1 minus x squared. So we just fill that in. Then we have our addition there in the middle. Then we have our constant multiple 3 in front. And then we just look up the derivative of arctangent, inverse tangent. So we go to our table, find inverse tangent there, and we just look it up. And it's 1 over 1 plus x squared. But we're using variable t, so it'll be 1 over 1 plus t squared. And I goofed. That's not an x. That should be a t because we're using variable t. So you want to keep your variable, want to be consistent with your variables. So a lot of times our derivative tables are given in terms of variable x or maybe u, but you just need to adjust it accordingly based on, what the variable is in your function. All right, let's try another example. This time using exponential and log functions. It's going to be the same game though. So let's say we wanted to differentiate the function 5 times e to the x plus x times square root x. And actually, before we go into this, the 5e to the x term that one's not going to be too bad. It's that x times square root x. And so our strategy here is we want to rewrite this. Right now, this is a product. It's x times square root x. It's a product. So if possible, we want to be able to rewrite that as a power function. And we can, because it's really just x to the power 1 times x to the 1/2. And when we have the same base term, how do we combine them into one power function? Well, we add the exponents. So it would be x raised to the 1 plus 1/2, or more simply, x raised to the 3/2 power. So rewriting this function, we need to get it into a format that we can do something with. The 5e to the x, that's okay. It was that x square root x that was kind of giving us a little bit of trouble. And so we rewrote that as a power function. So x raised to the 3/2 power. All right, so now we're ready. We can differentiate this thing. So let's just rewrite our function here, 5e to the x plus x raised to the 3/2 power. And the way our rules work, we look in the first term, apply the derivative to just the variable part. So that 5 is a constant multiple, so it stays out in front. Go to our second term, apply the derivative to just the variable part, so x raised to the 3/2. We're just going to differentiate that. And then do it. So e to the x. What is the derivative of e to the x? We go to our table. Derivative of e to the x we see is, very nicely, same thing, e to the x. So it doesn't look like you did anything there, but you actually did. So derivative of 5e to the x is 5e to the x. And then for our power function x to the 3/2, we bring the 3/2 down, keep x the same, and then we subtract 1 from the exponent. So we're left with just x raised to the 1/2. All right, so there's our derivative. Let's try another one. So one more here. H of t equal to t squared plus 1 divided by t plus 7 times the natural log of t. And as this is written, again, we're kind of seeing another issue here in that that first piece now is not a power function. It's not something that we know how to handle yet. So same strategy, we want to rewrite that as a power function. So how does that look? Well, when we have a fraction like that, what we can do is we can split up a fraction so that we take each piece of our numerator and put it over the denominator. So we can split this up, that fraction up, into t squared over t plus 1 over t. And now if we simplify each of those, t squared over t just simplifies to just t. And then 1 over t simplifies to just t to the minus 1. And so each of those is a power function. So if we rewrite our function now, we could rewrite this as t plus t to the minus 1 plus 7 times natural log t. And now we have 3 terms, and each of those terms we know how to do. Let's do our derivative, h prime of t. Rewrite our function here. And we're just going to go term by term, apply the derivative to each of our variable pieces. So in the first term, we're going to apply the derivative to just the t. In the second term, we'll apply the derivative to t to the minus 1. And then in the last term there, we'll apply it to natural log t. And want to look up the derivative of natural log, go to our table, and we see that it's 1 over x. Or, well, 1 over x. For our case, it'll be 1 over t. So we end up with derivative of the first term is 1. Derivative of that second term is negative t to the minus 2. And then derivative of our third term is 7 times 1 over t, which was our derivative of natural log. So just to see how all of these sum, difference, and constant multiple rules work with these elementary forms that we're going to be working with. All right, last one. How does it work with second derivatives? So let's say we have a function t cubed minus 2t squared plus 3t. And we're going to do the first derivative, and then we're going to do the second derivative. And let's just see how it works. And then we're going to evaluate those. So we have our function. We're going to differentiate. So that's going to give us our first derivative, which is 3t squared minus 4t plus 3. We want to calculate the second derivative of this, so we just do it again. So derivative, that gives us our second derivative, which we can write with those kind of look like exponents, but they're not quite exponents there. And then we just do the derivative yet again. So derivative of 3t squared is 6t, and then minus 4. And then we apply, so we have our first derivative, we have our second derivative, and then we want to apply, we want to evaluate each of these. So that's what this vertical line represents. It's our evaluate line. So we're going to do the derivative evaluated at -2. So what do? We take our derivative function and just wherever we see a variable, we plug in the number -2. And if we do that calculation, we end up with 23. So when we evaluate a derivative, the result is a number. And then finally, we want to evaluate the second derivative. Let's just see how that works. So we take our second derivative, we evaluate it at -2. That's what the vertical line means. It means we're just evaluating. And so we plug in. So we rewrite our second derivative there. But wherever we see a t, we just change it to -2. So we end up with -16 in this case. All right, so just a little bit to end there in terms of, how does this work with second derivatives? You just do the derivative again. And then how do you plug in? You just change your variable to the, to whatever number you want to plug in. So -2 in this case. All right. Let's stop. So next time what we're going to see, we saw all of our basic derivatives here. Next time we're going to see how do we handle products and quotients, and then we'll be able to use some of those rules to kind of prove some of these elementary forms that we looked at. And then we'll probably also get into chain rule a little bit next week. So that's a preview of things to come. All right. So just a reminder as we get going, our next exam is next week. So I posted on the course website, what it's going to cover. So it won't cover today's material, just cover up through on Tuesday. So have a look at that. If from the first exam you got marked with a P on a question, or maybe more than one question, you'll have the chance then to redo any of those on the exam next week. So for full credit. So make sure you understand what you got wrong. If you have questions, go to a recitation or come to office hours, and then just try again next week with correcting the mistakes that you had. All right, so we'll see everyone. Have a good weekend, and then we'll see everyone next Tuesday. Bye-bye.